Ben's just going to continue to teach us everything he knows. He's studied dust, so we're busting the dust myth.
So we were talking about, like, is dust made out of dead skin? And sure, some dust is made out of dead skin, but for my undergraduate physics research, I was working at the time it was a long baseline neutrino experiment up in the Homestake mine in South Dakota. And my research was to figure out how much dust was in the air, because that dust was actually made out of mine rock, which contains radioactive elements.
What does it mean to be radioactive? We just went over this.
Means that you've got an atom and it's got electrons flying around out here, and you've got a nucleus in the middle. When something radioactively decays, this thing in the middle breaks into two pieces, and you end up with two totally different atoms. And that releases energy. That energy is what we're trying to detect in this mine, and we just need to know how much of this energy that we're detecting is coming from the dust that was in the air and collected inside of the detector while they were building it, and how much is actually from the experiment where they shoot neutrinos from Chicago through 800 miles of rock all the way up to South Dakota.
So you're trying to detect energy created from a reaction in Chicago up in South Dakota?
Yeah, we're trying to detect particles created in Chicago and detect them in South Dakota. And the reason that these particles are hard to detect is they don't interact with anything. They shoot them straight from Chicago to South Dakota, but the cool thing about that is that the Earth's curvature is in the way. So when you look at this beam, you're looking at a gun that is aiming into the ground. Those particles travel through 800 miles of rock like it's not even there, and then you want to detect them on the other side. Well, if they don't want to interact with rock, they don't want to interact with your detector either, so it's really, really difficult to figure out if they actually showed up or not. So we put a lot of effort into finding all the other things that might be giving signals into this detector. A signal is just anything that you can detect, like either one of these nuclei decaying, or if a subatomic particle from the sun is flying through and just hits it. Like, there's lots of different areas where these reactions and these events could occur from, and we just need to make sure that the ones that we're actually measuring are the ones that we want to.
Okay.
Because there's lots of other things that we could be detecting, and we could end up saying totally the wrong thing if
so
we
you
do the math and the work to figure out what we're actually seeing.
So you're like fine-tuning to find one particular signal in a lot of noise.
Yeah, we're trying to find one of the quietest signals in a lot of noise.
And what's the point? So what would you know?
So one of the big things that experiment wanted to look at is what happens to these particles called neutrinos as they travel. Now, it doesn't make any sense to us, but one thing that math says is that as these neutrinos travel, they're just going to change from one type to another. Like, imagine that you have like a water molecule. We know that water is H2O, and those two hydrogens are always going to be hydrogen, and that one oxygen is always going to be oxygen. And that's just how it's going to be forever. Well, that's not the way that neutrinos work. Neutrinos just fly through space and change from one thing to another. And
what? They're just shape-shifting molecules?
Shape-shifting. And that was what this experiment was going to do. They want to see if we start with some number of one type in Chicago, do we end up with a different number of a different type in South Dakota? And how many of these have changed?
And so what'd you find?
I've got no idea. The experiment's still going on.
Okay.
That's an international... There's thousands of people working on that project. And there are literally thousands of people. Like, on some of the papers that are written for that, the whole first page is authors.
Oh, really?
It's a full page of nothing but...
That's a lot of people to collaborate with, like group work to the max.
Yep, and we collaborate with people from all over the world, collaborate with different universities in the U.S., different laboratories in the U.S. I was working with a guy who was working from China. He did a lot of research with that stuff. He went to school in Beijing, and he was teaching in South Dakota, and it was cool. There was people from all over the place speaking different languages, all coming together to try to solve a really hard problem. Do these neutrinos change types? We think they do. We think we can prove they do, and we'll find out next.
Well, humans... Well, it's like a step in evolution if we know whether or not these neutrinos change form. Like, we know so much more then about the composition of the universe that we've never known before.
We know that something that we didn't think happened. mean, if you look back 50 years ago, like, people barely had an idea what was happening with molecules or with atoms that make up molecules.
Yeah.
They kind of just thought that things were generally the way they were. But since the beginning of doing nuclear physics research, we learned that things don't always stay the same, and that there's huge amounts of energy in some of these reactions. I mean, that's where we get both nuclear energy and nuclear bombs. They're running on essentially the same energy, but in a nuclear reactor, we control the rate that we release energy, and we can harness that and turn it into electricity. We get really clean, good energy out of that. The downside is that this could also be used for nuclear weapons that obviously have huge impacts on lots and lots of people. So there's kind of a harmony that we have to find here, where we research and we can study as fast as we can, but we don't accidentally let people that shouldn't have the power to do this stuff actually have it. And there's just so many different aspects that we have to think about when we're looking at this kind of research. And
there's a whole ethical side of it.
Yeah, there's always an ethical side to research. I mean, what if we found out something that totally changed the way the world worked? I mean, what if somebody's research, like, people are always freaked out about black holes. What happens if we create a black hole in a laboratory and it sucks the Earth in? It's probably not going to happen. It's not the way the black holes work. But it's an obvious concern. If that was something that could happen, we would probably want to look out for what happens when people are doing black hole research, because it would be a pretty big bummer if somebody in, like, I don't know, let's just say they were at a university in California, created a black hole, and then sitting here in Utah, all of a sudden we just get sucked into it. That'd be a huge bummer.
That would be a huge bummer. There'd be no more race.
Yeah, we wouldn't,
We wouldn't breathe anymore. Naked would be gone.
Oh,
No
man.
more dogs.
No more dogs.
Quite
No more hamburgers.
Right? Ugh,
Shoot.
don't
The
want
sun?
that world.
Would the sun still exist?
The sun would still exist.
Oh, okay.
The sun's not going anywhere.
Would the ground, the earth, or just humans would be sucked in? Could it be a selectively suckable black hole?
Could. I don't know.
A selective black hole.
We don't know. We only know so much about it. We can only study black holes by looking at, well, not only study black holes, but when we study real black holes, we're looking at things that are light years and light years away from us in space. And we're trying to learn things we're trying to learn things about black holes using light that was created tens, hundreds, thousands, or millions, or billions of years ago.
What?
The universe is a huge place.
We're trying to observe the present moment by the only evidence we have is from way in the past. Wild.